Hello, everybody. Hope you're all doing good and staying safe. My name is Govind Bere, and the paper that I'm going to present you today is Blockchain Based Firmware Security Check and Recovery for Smart Inverters. And my co authors are Boan, Dr. Taisik Kim, Justin J. Ochoa, and Dr. Abdullah Al Hadi, and Dr. Jinjun Choi. And we are from Texas A&M University, Kingsville. And Justin is working at Sandia National Laboratory. Yes. The outline that I'm going to present today are the introduction and related work, specifically the firmware attack surface and penetration testing, blockchain software, security properties, and the proposed method and validation, and finally conclusion. Introduction. Smart inverter. Grid control functions such as fault right through, grid voltage and frequency control, and relative power consumption. These enable the remote monitoring control and firmware updates, which we can call also as energy IoT. Okay, these smart inverters are going to be installed more and more in the coming future, but there's going to be some security concerns like extensive data exchange is going to happen across the networks, and there's going to be multi-party access to the smart inverter, such as operator will be there, owner, vendor, utility. Okay, and legacy inverters have no security or at least few security functions. And if you come across the state-of-art defense strategies focused on the network-based security techniques such as network segmentation, encryption, and moving target defense. Okay, you can see the picture of the inverters over there, and this is some security sensitive layer of smart inverters. Okay, coming to the related work, firmware attack surface. Software related attacks can bypass the most advanced access control and security mechanisms. And you might have seen and come across numerous firmware vulnerabilities that are happening in the power electronic devices, right? So in our research, what we have, we studied, like you can see the attack in the December 2020, the solar wind supply chain attack. Okay, that comes under, like, we consider it as attack point one, the vendor access via a regular software update. And there is also an attack point 2, which is user or operator access via the remote interface. And there is an attack point 3, which is a physical access via the USB or flash drives or local area network. You can see the setup over there in the right side. Okay, yeah. So the attacker can attack from at the place of user access or the vendor access, or it might be a physical attack. All right. In the penetration testing, we have the experimental setup over there at the top right corner. Okay, you can see the TI inverter over there, and there is a IoT device also, which is Latapanda, and we also have a Code Composer Studio, which is running in the IoT device. Okay, and IoT device is running Windows on it. Basically, this IoT device access an interface. It takes information from the inverter and sends it to the blockchain. Okay, and the main reason of this slide is we have done some penetration testing. We have changed the files, the value of the relay in the main.c, which is a firmware file of the TI inverter. And after doing so, you can see the oscilloscope, right? It's the normal case, and the other one is a malfunction which has been caused by a firmware attack. But we have done it, yeah. Blockchain security properties. Coming to the blockchain, right? Blockchain is not something which is related only to the Bitcoin, only to the Ethereum. This is something different. This is a cryptocurrency blockchain. But the blockchain that specifically I am talking about here is the blockchain, uh, which is an emerging security platform which is used for the auditing and the tracking the transactions, and which is combining the state-of-art trust mechanisms, distributed database, and cryptography and consensus algorithms. Okay, so this is used. This is also called as distributed ledger technology, and the technology that we have used for the paper is Hyperledger Fabric blockchain. And some of the properties of it are like permission, it's a private network, and we maintain the data integrity, and smart contracts define a set of rules that govern the transactions within networks. Like, these transactions should follow these rules. Okay, and the distributed ledgers avoid the single point of attack, whereas the centralized servers, which in case a single point of attack happens, everything goes failure. This doesn't happen in this. The proposed method is that a cooperative multi-party security ecosystem under the blockchain network. Basically, we have many kind of clients, the inverter, vendor, user, onboard security module. These are all authorized persons which provide data to the blockchain network, and they upload and access the data and also share the data between themselves in the ledger. Only authorized vendors are able to do this. And what we're going to compare here is we will compare the hash of the firmware and also the version number of the firmware. Therefore, the blockchain network will provide the increased visibility into the methods, applications, and services, and ensures the integrity, authenticity of the software assets. And software and the firmware records that are archived and tracked in the immutable distributed ledgers. Basically, immutable means we cannot like change something or delete anything. Proposed method. As I told you, the proposed method is we have an onboard security module, which is IoT device as of this case in this particular paper, which is Latapanda. So this Latapanda is right. This is helping us to take the data from the inverter, and we are using the SHA-56 as an hash algorithm. This will convert the firmware file into the hash, and it will send that particular hash and also the firmware version. There is also something called a version to the firmware because there might be some updates that will be happening. So we send the both the hash of the firmware and also the version to the blockchain network. What the blockchain network does is it will compare both of the hashes, the hash that has been received by the user and also the hash it has already received by the vendor. If they both match, what's going to happen is it's going to say the authentication is true, there is the validation is yes, and status is normal, as you will see in the further slides. Okay, so yeah, this is all about the OSM, and there is actually an algorithm which we have developed for this firmware check and recovery. As you can see in the first step, initialization, all the the vendor will be sending the firmware original firmware's hash value and what is the current version, and the inverters, the IoT, the current users, they will send what is the firmware's hash value that they have currently and what is the version they have right now. So once they have sent these values, right, before sending these values, OSM is actually calculating the hash value. And the hash that we're using is SHA-256. Basically, this is one of the bestest hash algorithms used right now in the market. So as the blockchain compares, right? No, blockchain will just compare and do the verification as yes, and status is normal. If the status is malfunction, it means that there is some mismatch and the validation is obviously no. And then automatically the OSM module will understand that there has to be the patch generation, and then it will generate the patch. I mean, like it's gonna, there's a Python program that we have developed. What it's gonna do is replace the whole firmware file which has been corrupted with the original firmware file. Okay, and so that we get the the hash of the firmware which is matching with the vendor's firmware. This is the smart contract I told you previously, right? So basically this one is the rules that we are writing for the transactions to make. So in a transaction in this particular project or in this particular paper is that we only can send the asset ID, the firmware hash, and the version and the verification tag and the status. We cannot send any other values, and this should be the order of it, and this should be the format, and the JSON is the format of it. If somebody is sending in some different direction or some different values, it will not be accepted. And there is something called consensus. I mean, if you go deeper or look into some Hyperledger fabric, you will get to know about consensus. So the validation of all the things that I've told you is this. So as you know, the experimental setup, we have a TI inverter, which is solar PV micro inverter C200. So this one is connected to the load and some oscilloscope. Okay, and it is also connected to the IoT device, and this IoT device is sending the information to the blockchain, which is actually running in a particular laptop that we have set up, which is actually server for the blockchain, which acts as a blockchain server. Finally, what's happening here, what we're doing is that I'll tell you, it will be clear in the next slide. Okay, so as you can see, this particular screenshot in the right side is the list of the transactions that are happened in the blockchain initially, right? So the first transaction is sent by the OSM module. Hey, this is the firmware hash we have. So this hash has been checked with the hash of the vendor, and it was a match. And then the verification was yes, and the status is normal. And the next, we did the reverse engineering, that is the penetration testing. And so we changed the relay value and the firmware has been changed. So as the hash value has been changed and it is a mismatch and the verification is no and malfunction, and immediately the OSM, that particular fpatch.py Python program will run in the IoT file, and that particular firmware file is replaced by the new firmware file. Then again, the new data has come. The firmware hash will be sent over to the blockchain and also the version. Uh, it is yes, but still malfunction. Then again, the version and the hash has been resent, but now, so everything is set. So it's yes and normal. So yes, that's all. As a conclusion, I would say that we provided a potential attack surface for the smart inverters by doing the reverse engineering and showing the vulnerabilities that might happen in solar inverters, smart solar inverters. And we have also provided a blockchain-based firmware security check and recovery framework and validated it by an experiment. The proposed framework can be implemented in smart inverters to mitigate the potential firmware security threats from attackers, thereby significantly minimizing the inverter restoration time and cost. And future works that we are doing include malware attack defense and patch generation of multiple smart inverters. I would like to thank from the bottom of my heart. This work was supported in part by the Department of Energy under the award number, as you can see over there. Funding was provided in part by the US Department of Energy, Office of Energy Efficiency and Renewable Energy Solar Energy Technologies Office. The views expressed in this article do not necessarily represent the views of the DOE or the US government. Thank you so much for spending your time attending my presentation. And I would love to take your questions. And you can ask your questions through the platforms that you have been provided in the by the APEC conference. And thank you so much for this wonderful opportunity. Have a good day.